we have here is a rational expression, all right, that's less than 0. We got negative 3 on the top, 2 minus x in the bottom. First thing I want to do, guys, is I hate when things are out of order. So the first thing I'm going to do is this, and I hate having the lead term positive. I hate it. And I'm going to do this. Now, you don't have to as long as you track your table correctly, okay? The nice part about doing it my way is what's a negative negative? Positive. So we can start by getting it to here. I can identify the zeros in the asymptote. First of all, there are no zeros. Because if we look at the numerator, what makes the numerator 0? Nothing. The numerator is always 3. Then we can look at the asymptotes. I'll do that in red. What makes the denominator 0? X can't be 2. And everybody, if you go all the way back up to here even, you'd still make that same judgment on that denominator, right? It's still 2. All right. There's 2 ways to do this. I'm going to do it the table way because the table way works every time. It is not the easiest way to do it this time. So I'm going to take all this stuff, and I'll put it up, we'll group it, we'll get it up over here. Table method says this. I have x, and I know I have to have 2, and I have a result over here. There are 2 factors this time. Now, I know for a fact if you're trying this problem on your own, very few people factor. I would argue that then your columns, if you didn't factor, your columns would have to be this. And guys, well, you got to have negative 3 in here because guess what the negative 3 always does? So negative 3 is always negative. And if you have 2 minus x, I look here and a number left of 0, how about negative 100? That's a positive. How about positive 100 to the right of 2? That's a negative. Our results here are negative, positive. We want the result of our function to be negative, less than 0. This works in the black. So even if you don't factor, this works. All right? I'm going to go back and use my factored ones now. All right? It doesn't change much of anything, except I have positive 3, and I have x minus 2. So it's positive, positive, and I might not even put 3 on my table then. All right, but I'm doing it so we see it as a factor. Negative 100, so this is negative, so it's negative. Positive 100 is positive. Either way, you notice it's the same. You notice I didn't erase the result area. Oh, I wrote 0 here. Let's back up. This is a huge mistake. How about undefined? I'm sorry, that's an asymptote. All right, so the question then becomes is where is this result less than 0? Where is it negative? It is negative in this right here. So it's going to be x is an element from negative infinity to 2, not including it. There is an easier way with this problem, and I am going to talk about it. When we have a problem like this, there is an easier way, and sometimes it works, so this is one of those times. Does everybody, let's go back to this problem, right? We're going to bring this over here and talk about it. At this point, do we all agree with that it looks like that? 3 is always positive, right? I look at this and know there's only 1 x in it. So my question then is hey, if this is always positive, I just want to find where the denominator is negative. So I can simplify instead of doing this whole table. This time, knowing and understanding math, I can simply do this. And I know x has to be less than 2, which is what this is, right? Because we think on our number line, it looks like this, right? X less than 2, which turns into that interval. 2 ways to do this problem. Let's try another one. All right. The very first thing you have to do is identify the asymptote. You always got to say, where's the denominator undefined. The asymptotes this time are at x equals 4 and x equals negative 7. Guys, no matter what, those values can't be part of your solution. You can't divide by 0. Secondly, we got to look at the numerator and say, hey, what are the zeros? Well, we can see just by inspection that negative 1 makes it 0 and positive 3. These become the 4 values in your table. These become the 4 places that separate your intervals for inspection. 4 numbers, guys, means we have to check 5 intervals. All right, so we'll start setting up our table then. All right, so I'll set up my values in descending from the smallest to biggest. So negative 7 is the next value I need. Negative 1, 3, and 4. 4 is an undefined, and negative 7 is an undefined. And I have my 4 factors from my rational expression. And some students don't like that I write them kind of at an angle, but otherwise these tables get very large. And I know the other 2 are zeros. So first of all, everybody, I want you to understand that negative 1 and 3 are solutions this time because we're allowing it to equal 0. So negative 1 and 3 will be part of your solution. All right, and maybe I put a little red check mark saying, yeah, these are in it. All right. And now I have all these intervals to check. Holy cow. 1, 2, 3, 4, 5 intervals I need results on. I got to know whether they're positive, negative. TD picked that he wants them positive this time, so we're looking for positives in those 5 blanks. I think of a number left of negative 7. How about negative 1,000? I think that in my head. Negative 1,000 plus 1, negative. Negative 1,000 minus 3, negative. Negative 1,000 minus 4, negative. Negative 1,000 plus 7, negative. That's just the sign of the number. I don't care about its value. When I multiply 4 negatives, negative times a negative times a negative times a negative, that's a positive. And everybody, I typically don't write the value here because it gets really mucky fast if you have a number right. So, or write it to this further out so it's away from the column. In between negative 1, negative 7, I pick negative 4. Negative 4 plus 1 is a negative. Negative 4 minus 3 is a negative. Negative 4 minus 4 is a negative. Oh, negative 4 plus 7, positive. That's a negative. Between negative 1 and 3, guys, pick 0. Because then you can just look at the, as long as you've factored it, it's pretty quick. So this is a positive. In between 3 and 4, how annoying. How about, and I can't stress this enough, 2 examples. It's not always alternating, guys. It is not always alternating. Greater than 4, I put in 1,000 in my head. 1,000 plus 1 is positive. 1,000 minus 3 is positive. 1,000 minus 4 is positive. 1,000 plus 7. And I'm putting 1,000 in all these binomials at the top of the column. And I'm just deciding the sign result of it. Now, where is it? We decided the 0 is okay. It has to be greater. This result is positive. All right, so this region, this region, this region. All right, so it goes from negative infinity to negative 7. It can't include negative 7 because a negative 7 is an undefined. It's an asymptote. And it goes from negative 1 to 3, includes both endpoints, so those are not open. They are closed. And the last one starts at 4, can't include 4, and goes to positive infinity. So we have this. Let's do a little factoring today. Keep us in practice. Did we all agree it's 4 and 1 on the top? And negative 8 and positive 1 on the bottom. And I did this on purpose, everybody, because we identify asymptotes first. We look at the denominator, and the asymptote is x equals 8 and x is negative 1. Then we identify the zeros on the numerator. We get x is negative 4. And you're tempted to write, and I'll do it in a different color, x is negative 1. But x is negative 1 is already an undefined number. It can't be a 0. So our table this time will have 3 values. It'll have negative 4, negative 1, 8. Our table will have 3 values. And I'm going to do it 2 ways again. On my x value, I said negative 4, line to 0, negative 1, line to undefined, and positive 8, line to undefined. And this is the result. I want to do 2 things. First of all, I'm going to put in the columns x plus 4 and x minus 8. Those 2 first. And everybody, I'm going to put the same, I'm going to put x plus 1 in for a second here in blue. Everybody, I want you to think of something. Every time x plus 1 gets a value, do you agree the sign of this and the sign of this have to be the same? Right? The sign of x plus 1 is the same top and bottom every time we check an x value. If they're both positive, it's positive. If they're both negative, negative times negative, it's positive. Thus, everybody, I know if I have a repeat like this, I can ignore these in my table. Because I know for a fact, no matter what happens, they might both be negative, but their result is always positive. So when I make a table then, I literally do not include x plus 1s. I don't have to this time. They kind of cancel, but realize that negative 1 can never be a solution. All right? It's a hole in our graph. All right, let's see if I don't know if it alternates or not. I'll have to check. I think of a big number. I think of negative 1,000. I plug that in. I get negative, negative. I get a positive. Oh, it's going to alternate. It's going to alternate. I think of negative 2. I get positive, negative. It's negative. I think of 0. I get positive, negative. Oh, wait. Ha! It doesn't alternate, does it? It's negative. I think of huge positive number. 2 trillion. 2 trillion plus 4 is positive. 2 trillion minus 8 is positive. All right. That's my results. I want my hunk of junk to be less than 0, which means I want my result to be negative. Everybody agree? My result has to be negative. So I look. I have a result negative here, not equal to 0. Not equal to 0. And I have a result negative here. Couple ways to write this. I'll write it both ways. One way to write it is just to write out the intervals. Negative 4 to negative 1 and negative 1 to positive 8. That's one way to write it. All right. I might write it this way, and that's x as an element. I might write it this way. Negative 4 to 8, x cannot equal negative 1. All right? Both ways are right.